Okay, hi everyone. Welcome to my session. Today I'm going to talk about the Primus reference architecture for training at scale on AMD GPUs. Yeah, so first I would like to talking about the trend and the problem we're facing today. So models are scaling fast. Starting from 2023, when the first version of the ChatGPT coming out, all the community are looking forward to build their own open source model, right? So if we look at today, actually there are two more open source models just released this week or the last week. There are 15x total parameters grow in the last 3 years. This is a huge jump, right? And then I think the trend is continued to further grow, and everyone see that pre-training, all those model training are the foundation for intelligence that the model can, or the model capabilities are today. So we're continuing seeing those trending, and it gives us a lot of challenges in today's AI infrastructure for training at scale. We're talking about like 100K plus GPU training for one model today, yeah. Okay, so what's our solution for this problem? My answer is that we need to do the scaling efficiency with both hardware software co-optimization. So if we look at today, if you look at the hyperscaler, the data center, we see all the computes, accelerators, storage, and networks, right? Those are piled up at the scale, but simply pile up won't work. We know that there are a lot of issues today we need to put together, understanding how to coordinate between the compute, communication, and the storage. So people coming up with a topology that to organize all those accelerators together, right? On the hierarchical, that's the three layer of fat tree. Today, with bigger switches, we can do 2 layers of the fat tree. But still, if you think about to scale to 100K GPUs, there's going to be a lot of hops between all those accelerators. So instead, I think we need to understand all those topology, all those cross layers of the different problem we are facing. We need to design all the software piece to make the system more efficient, from the sharding strategy, from the efficient model architecture design, towards all those stability at cluster scale as well. So this is not simply one solution, one answer. I think it's involving a lot of efforts. So in terms of GPU utilization, we look at 2 key metrics. One is the MFU, which represents what kind of peak flops you can run for workloads. But on the other side, we also look at the goodput. Goodput means what kind of real time you're going to be efficient running this model. Sometimes the cluster will have some hiccup because different kind of failures. So those will be the downtime. So we are looking for 2 key metrics at the same time. And our solution at AMD is we care about 4 pillars. The first thing is the user-friendly. There are a lot of stacks across the whole training. And I understand that if you want to start, people always want a out-of-box performance, not doing a lot of add-ons on himself, right? So that's the first goal that we want to achieve is, can we run a single command, let people start to train their model? The second thing is the performant. Perform means that different kind of model, language model, multimodality, diffusion-based model, even the recommendation system, right? All those today's multimodality media, they are using recommendation system. It's still the largest traffic, I think, today for internet service. And then low precision. We also introduced FP8 training, and also we are also supporting FP4 training for Llama AB at the current stage. And then we talk about scalable. right? As model parameters continue to scaling, our cluster size also continue to scale as well. And we are hearing about the gigawatt hyperscaler AI factory. Those are the place where we see hundreds, thousands of the GPUs. But in the system, not only GPUs, you also have the switches, CPUs, and other components, optics. So total together, probably it's a couple X more devices in the whole cluster. And last one, so we're facing a huge system. We need to provide the stability, how we can make sure we have the fault tolerance to run the long journey of the training. Usually it takes 2 months to 3 months. How you can guarantee that you can make use of most of the time of those accelerator T-flops. So our solution here is very clear. We want to cover the end-to-end life cycle of the training. So from the system level design to the system level preparation, how we do the trial run, right? People will run different kind of ablation study on the small size and then scaling up, right, to follow the scaling law. And then performance optimization alongward, right? And then we have the production scale run, to launch the 1 month, 2 months, pre-training stage. And then we provide all the solutions or tools to support those, right? From the projection to let you understand what kind of scaling law you can facing, what kind of roofline you can reach, right? And then to a set of other tools like Primus Bench to let you to calibrate on all those compute, and tuning agents to let you to understand, and leverage all the expertise we build up to, running through all those training cycle. Of course, we also provide the support on the RL side as well. And then Primus Core is what we provide here as the best recipe that we support the training at scale. And also today we build up the RL further to extend our support on the most popular RL framework that here in the open source community. Everything is built on our ROCm stack, and you leverage all the best performance that we can get from all those softwares and libraries. So as I mentioned that we have a very easy to start one CLI command line, then you can start the training process. We support 4 most popular backends: Magtron, Torch Titan, JAX Max Text, and diffusion model. And then we have 80 YAML file that you can pick. Those contain the most popular open source model. You can start with all those YAML file to run at the best recipe that we provide, and then iterate on those. And then we provide all those optimization pieces, patches onto our Primus ecosystem, or Primus software stack ecosystem. Especially the kernel level, we provide like the DPP, like the better attention implementation as well. And then our CLI command line, including the pre-flight check, projection, and other things that let you to quickly go through the life cycle of the model training. Okay, performance data. Yeah, at today's AI, Advanced AI Day keynote speak, Vamsi already mentioned that from the ROCm 7.0 to today, we see a 2.4x of the performance optimization uplift. It's come from the parallel strategy. We are developing more efficient sharding strategy like the pipeline parallelism and the better memory management, as well as more optimized kernel for the training purpose. So overall, in addition, we have a very fast-paced release cycle. We released our training Docker in a 2-week bi-weekly cadence. So every 2 weeks, we were updating our model support, our latest performance libraries with the best recipe we can provide it. So far, we see a lot of downloads from the community, and it's keep growing. So we will continue these efforts. And also, we provide a non-Docker environment pip install as well. So it's supporting different environment to pick up this software stack. Then the key driving strength behind this performance uplift is we continue to release our best support for the MOE model training. So we released the MOE package. And within the MOE package, we did a couple of the best effort to reduce the occupation on the communication and on other part, right, to let the GPU continue to run in the busy mode. So one thing is that in the MOE architecture, we know that there's a lot of the dependency on the CPU side, mainly on the indexing and other stuff. You're waiting for CPU to launch the next kernel. And we are using some of those techniques to remove those of the MOE dependency, so make it sync-free MOE. And the second thing is that we're also developing a Yoco EP, that's a version of the DPP. The main motivation is that today you are facing different kind of NICs. We have Broadcom NIC, we have AMD Pensando NIC, as well as other NICs. And then every time, because of those current DPP, they leverage the GPU direct. So you have to, adapt different kind of AI NIC, different kind of NICs with your GPU. So it takes a lot of time to go through that, right? Instead of that, we use Yoco EP to release some of those effort to the CPU side. Therefore, you can have a quick adaptation for different kind of NICs. The third thing is the sharding strategy. So for MOE model, there are two directions to sharding your model. One direction is getting bigger model. It means you have a deeper layer, more number of layers, deeper pipelines. So we're developing a 1F, 1B, and all-to-all overlapping together. So you can do your sharding while you overlapping your computation and with communication more efficiently. And one more thing that we recently worked on is the mega kernel. So as we continue to develop this, we find that even we do this overlapping between the compute and communication, there's still some risk condition that will reduce the efficiency of your kernel execution. So instead of we build a mega kernel that we fine-grain tuning the compute and communication within one kernel. Therefore, we can pipelining those compute and the communication. But one problem is when you start to do this, you cannot continue to leverage the assembly level heap plus LT kernels, right? Instead of we using the agentic way to write our own fly DSL kernel. So those kernel has as good performance as the assembly one or close to that performance. Therefore, we see that for the forward, we have 1.6 performance uplift, and for the backward, we have the 1.13x uplift for the end-to-end performance. We got 1.4x uplift. So that's a huge jump. So it's just about to release with the latest Docker release. You will see in our Primus Turbo library. Okay. The other thing is that the memory, right? So we know that there are a lot of memory footprint is on the activation side, right? So how we can further understanding all those memory consumptions, right? Because sometimes if you hit the memory bound, you're gonna slow down your system because there are a lot of checkpoints there are a lot of activation, recompute, and the stuff coming, right? Or you do offloading, then loading back. So we provide a lot of strategic optimization, and we also leverage our tool, right? You can visualize how well you're doing in your pipeline parallelism. What kind of bubbles you're seeing here? What kind of memory consumption to align with all those bubbles? And then with all those, you can further to tuning your sharding strategy. And then we do a strong scaling. So today, if we look at the strong scaling, although we only do the experiments to up to 64K, but you can see we have a pretty good a strong scaling all the way to the 64K with a minimum performance drop within the allowance. Okay, all talking about is about the performance optimization, sharding strategy, kernel optimization for the large-scale model training. The other thing that we are facing today is the stability, reliability, right? Because you are training for a long time, a month or 2 months, so you're facing a lot of challenges that the system, any of those GPU, CPU, or even the switches, optics, gonna have some hiccups. Then you're gonna delay your training process. So instead, we're building a more towards agentic way to help us to detect and to do all those preventive solutions along this path. So first, I think it's we need to build a very good telemetry or observability layer that we can understand how everything going within the cluster from GPU to CPU to optics. And on top of that, we are running all those kind of data analysis and understand where are those potential risks of the failure going to happen, right? And then we keep this loop again running on the back end to understand the whole status. And then one more thing that the team did is that we have another layer of the fault tolerance today that instead of stop the training and loading the checkpoint again, we have a dynamic way to elastic shrink our cluster size that we are not stop the training. While we bring up the extra nodes back, we can continue to expand the training. And with this way, there's no waste time. You are continue running this cluster as long as you have enough set of the GPUs. Okay, so here come with the conclusion. I think today that a training system is not only about the efficiency. I think we're talking about at the same time that the model is continue running and with bigger size and trillion level parameters. So we have to think about how to run more efficient sharding strategy, kernel optimization, combined with the stability at the same time. So Primus provide all those solutions at one place. So we will continue to evolve in this journey, and we're looking forward to more excitement with our recent rack scale 455 release, and all those optimization gonna go to one level stage ahead of us. Yeah, thanks for everyone.